Hello everyone, my name is Elisabeth Spiraki from geoengineer.org. I am pleased to introduce you to April's 2017 online lecture organized by the International Society for Soil Mechanics and Geotechnical Engineering. This month, Professor Leroy will be talking about compressibility and consolidation of clays from lab to field conditions. Professor Serge Leroy obtained his engineering degree from the Institut National des Sciences Appliquées, Lyon, France, in 1970 and his PhD from Université Laval, Quebec, Canada, in 1977. He worked 2 years with the consulting firm Terratech, Montreal, and then joined Université Laval, where he spent his entire career as professor in the Department of Civil and Water Engineering. His main domains of research have been soft clays, microstructured soils, compacted soils, embankments on soft soils and landslides. He was the 1999 ranking lecturer. Note that after the completion of the webinar, Professor Leroy will be happy to answer any questions posted on the ISSMG Q&A platform. The platform will remain active for 2 days. It is located below the present video and you may access it with your GeoWorld account. Enjoy the lecture.
I first would like to acknowledge the International Society of Soil Mechanics and Geotechnical Engineering for inviting me to give this presentation on compressibility and consolidation of clays from lab to field conditions. This is a topic which has been discussed for more than 80 years, but which is still discussed. In fact, the presentation will be divided in 4 sections: introduction, laboratory conditions, field conditions, practical conclusions. And as the introduction, in fact, the problems associated with embankments on soft clays are essentially stability, settlement rates, lateral displacements. In fact, for this presentation, we talk only on settlements and settlement rates, which in other words, we'll talk about compressibility and consolidation. Just a few words. Usually, the compressibility of clays is represented in a E log sigma prime V diagram and characterized by the pre-consolidation pressure, which is defined by sigma prime or sigma prime Vy, and essentially the compression index C sub C. With time, in fact, when we load a soil, there is some settlement, some decrease in void ratio associated first to pore pressure dissipation, and that's reconsolidation, but then settlement continues during secondary consolidation. And this secondary consolidation is characterized by C alpha E, which is the slope of the curves in a E log T diagram. In fact, the general equation for one-dimensional consolidation is the one here on the right, and it shows that the strain rate is directly related to the pore pressure, which means that if we have movements, settlements during secondary consolidation, that means that there are still excess pore pressures. They are small, but still there. Laboratory conditions, in fact, Mesri and co-workers have demonstrated that C alpha E is proportional to C sub C for a given clay, Here, the ratio is 0.03 for these two clays. And they also have shown that for inorganic clays in general, in fact, this ratio is always equal to 0.04 plus or minus 0.001. For granular soils, it's smaller, but for organic soils, it is larger. So this is an interesting characteristic. Now a few words about the CRS, constant rate of strain odometer test, because I will refer to this test and maybe some people are not familiar with it. In fact, we have a specimen in a odometer cell which is loaded on a press, a triaxial press, at a constant rate of strain. The objective of this test is to get a compression curve within about 2 days. The advantage of this curve and of this test is that the stress-strain curve is continuous. So the pre-consolidation pressure is well defined. In this test, in fact, we measure the pore pressure at the base of the specimen, UB, and the vertical effective stress is equal to sigma V minus 2/3 of UB. In fact, there are limitations when the pore pressure at the base is too high. What has been shown by several authors is that when we increase the rate of strain, in fact, the compression curve moves towards larger effective stresses as indicated on this figure. Here is about 10 minus 8 second minus 1, and here it's 10 minus 5 second minus 1. So from this kind of set of curves, what we call isotax, which are relevant for stage loading tests as a conventional odometer test, in fact, can be shown that this set of curves here can be described by two curves. One which is showing the log, says the log of the pre-consolidation pressure or vertical yield stress versus strain rate, and a normalized effective stress strain curve in which the vertical effective stress is normalized with respect to the pre-consolidation pressure associated to the strain rate. The slope in the log-log diagram can be defined by alpha. In fact, we can show that alpha is equal to C alpha E over CC. So that's the same thing, which means that for inorganic clays, for example, C alpha or C over CC or alpha is equal to 0.04, typically. What does that mean? That means that, in fact, the change in effective stress when we change the strain rate by 1 order of magnitude is typically 10%. Remember this number. So it's smaller for granular soils and it's larger for organic soils. This is an example on batiscan clay, and you have here the vertical effect stress or pre-consolidation pressure versus strain rate in log, and alpha is equal to 0.048 in this case. These are, for the same clay, normalized compression curves, and you can see that all the data, except these two data which are being obtained at too large strain rates and which gave too large pore pressures. Otherwise, all the data are in a small range considering that we are working with a natural clay. This is another example, Berthierville clay, and the curve in the middle here is the relationship between the vertical yield stress and the strain rate at 20 degrees, and here you have the normalized stress-strain curve. In fact, Watabe et al. Have shown that the relationship is not perfectly linear in log-log, but is curved as shown here. And in particular, there would be an asymptote at a pre-consolidation pressure equal to 70% of the pre-consolidation pressure at a strain rate of 10 minus 7 second minus 1. 10 minus 7 is typically the strain rate which is obtained after 24 hours of. So it will be a curve and not linear. In fact, we observe this earlier, and you can see on this data that alpha is equal to 0.04 between typically 10 minus 8 and 10 minus 6, which are strain rates usually obtained in laboratory tests, but that at larger strain rates, the slope is larger and it is smaller at small strain rates. And this is what I just said, and this is consistent with what is shown here. These test results have been obtained by loading specimens in the normally consolidated range and then unloading just a bit to a given OCR. When the OCR is relatively small, as 1.5 here, what happens is that after unloading, the soil swells a bit and then starts settling again in secondary consolidation. However, when the OCR is high, for example 8 here, at that time there is swelling due to pore pressure dissipation, and then the soil continues to swell in a kind of secondary swelling. So, in fact, the strain rate model I was talking about before can be generalized in this form here, where we have here secondary consolidation, but below an indifferent equilibrium somewhere here, in fact, we have a secondary swelling. So that means that it's a kind of generalization of the stress-strain rate model. Practical implications of the strain rate model in laboratory conditions. First, if during a CRS test we change the rate of strain, at that time we move from one curve to another curve. And this is shown here where you have two strain rate which have been used, epsilon V1, epsilon dot V2. And so that's logic with the strain rate model. Now, if we come back to the CRS test, I told you that typically it's completed in about 2 days, and the strain rates usually used are between 3 and 5, 10 minus 6 second minus 1. I told you also that after 24 hours, the strain rate is typically 10 minus 7 or slightly less, which means, or which explains, that the compression curves obtained in CRS tests and in conventional 24 hours tests are different, with the CRS test giving a compression curve at higher effective stresses than the 24-hour test due to strain rate. This has been observed on many clays, here Japanese and Quebec clays, and it can be shown that the strain rate is in this order slightly less than 10 minus 7, as I was saying before. And because of that, in fact, it appears that the pre-consolidation pressure obtained in CRS tests is typically 25% larger than that obtained in conventional 24-hour test, which means that if you want to change test for a CRS1, be aware that your calculated settlements will be much smaller than with the 24-hour odometer test. And this has been observed in Quebec, Japan, Finland, Italy, UK, Sweden, Hong Kong, Singapore. So it's quite general. Another aspect related to that is about what happens within a specimen. And Mesri and co-workers made special tests with specimens, with four subspecimens in series, with the subspecimen 4 being close to the impervious boundary and the specimen 1 being close to the drainage boundary. And they loaded such specimens they loaded it to the same stress increase, and the results here are typical of what they observe. The specimen 1 is going to relatively high stresses, while specimen 4 goes to much smaller stresses. And the subspecimen 2 and 3 are somewhere in between. In fact, this can be explained as follows. Close to the drainage boundary, the strain rate is initially high, and so the soil goes to high strain rate curve, while far from the drainage boundary, as for here, in fact, the strain rate initially is relatively much smaller, and so the effective stress goes to lower effective stresses. And when the consolidation progresses, at that time the strain rates become more homogeneous within the specimen, and all the curves converge. So the fact is that the subspecimens in one specimen are not following the same stress-strain curve because of strain rate. So and we could add that the end of primary compression curve, which join this point and this one, in fact, is unknown from the soil itself. From these results, it's possible to define a set of isotac, constant rate of strain curves, and the subspecimen 1 goes to high strain rate, 10 minus 5 here, while the subspecimen 4 goes to the curve 10 minus 6 about. So this is consistent with the strain rate model. Another aspect which has been discussed a lot is to know what happens if we have layers, clay layers of different thicknesses. And this problem has been raised by Ladd et al. In 1977, and there are two extreme hypotheses. Hypothesis A considers that there is no viscosity during primary consolidation, and that whatever the thickness of the soil layer and whatever the strain rates, in fact, the curve, the stress-strain curve followed is the same during primary consolidation. On the other hand, there is hypothesis B, which considers that there is viscosity during primary consolidation as during secondary consolidation, and that consequently the compression curve followed in a thick specimen will be below the one obtained on a small specimen. So at that time, that would be the small specimen thickness, and here the thick specimen thickness. Another aspect, but which is the most practical problem, is that with hypothesis A, we will have a strain time curve like that, like this one, with the same settlement, say, at the end of primary consolidation, while with hypothesis B, the settlement time curve will be as the dashed line here, with a end of primary consolidation, which will be reached here. So the practical aspect is this delta epsilon, which is the difference in strain and then in settlement between that of a small thickness sample and a thick thickness sample. So that's a question which was raised in 30 years ago. This aspect has been examined by Mesri, who compared the end of primary consolidation of specimen having a thickness of 125 millimeters and specimens having a thickness of 500 millimeters. So they loaded these two specimens with different heights and obtained this compression curve. The green is for the 125 millimeters and the blue is for the 500 millimeters. They considered that the two curves were similar and that this was proving that hypothesis A is the correct one. However, we can raise few questions. Which difference are we talking about between the specimen with a thickness of 125 millimeters and that the one with 500 millimeters? In fact, hypothesis B, which is at the other extreme gives a delta E of 0.06, which is not that much. But there is something more important, is how the end of primary consolidation is defined. In fact, Degago et al. In 2009 examined this data, in fact, and considered that we could define the end of primary consolidation at a given degree of consolidation. So, for example, 96% in figure A and 93% in figure in figure B. And so they looked at the results, but at the same degree of consolidation. And they came with the red curves for the 125 millimeters rather than the green here. The red curve here rather than the green here. And at that time, they found that the difference, there is a difference between the two specimens, and that this difference is not far from 0.06. And they concluded that hypothesis B is the correct one. Hypothesis B is consistent with the strain rate model previously described. So, clay behavior is controlled by an effective stress, strain rate relationship, and in fact this model can be extended but also can present limitations. Extension, in fact, the strain rate effect applies to all aspects of soil behavior and in particular to the underhand shear strength of the clay. And this has been shown by Kulawi and May, which are showing a normalized underhand shear strength versus strain rate, log of strain rate. And they come with, as a conclusion, that the underhand shear strength is varying typically by 10% per log cycle. Remember, 10% is also the change in pre-consolidation pressure per log cycle. So we get the same number. Another extension is that the viscous model, the strain rate model, can also include the effects of temperature. And this has been shown by several people, including here, but in particular by Eriksson, who performed CRS tests on the Swedish clay at different temperatures. And the results are shown here. You can see that the smaller the temperature, the larger is the vertical effective stress. And the pre-consolidation pressure, or vertical yield stress, is plotted here as a function of a strain rate. So there is a decrease with increasing temperature. And it has been shown that, in fact, the relationship obtained on Luleå clay is about the same as the one obtained on a variety of clays, as you can see here. So, in fact, the pre-consolidation pressure or vertical yield stress, which was a function of strain rate, is also a function of temperature. And this is shown here for the Berthierville clay, where you have the line in the middle at 20 degrees, the upper one at 5 degrees, and the lower one at 35 degrees. But when the vertical effective stress is normalized with respect to the pre-consolidation pressure associated with the temperature and the strain rate, at that time, all the data come in a very narrow band. So it can be said that, in fact, the strain rate model can be extended to temperature. And we have the similar numbers for different clays in terms of effects of temperature, but also effects of strain rate. The alpha is 0.04 for inorganic clays. And there is no doubt that there is something fundamental behind this. Limitations now. The strain rate effects applies to plastic strains rather than total strains. Consequences are relatively small in most cases, but fundamentally it's important to indicate that point. When we have a clay which is during secondary consolidation here, so with a decreasing void ratio, if we stop the strain, in fact the strain is constant, the strain rate is zero, so it's constant, and so the effective stress should be constant. It's not the case. During this test with time, in fact, the pore pressure increases. And so the effective stress is decreasing. And the explanation is given here. If we have soil at a point such as A here, in fact, the plastic strain has a tendency to creep, in fact. The plastic strain has a tendency to increase and so to go here. But as the strain or void ratio is constant, in fact, the soil has to compensate with an equal value of elastic strain, which is shown here. And to have this, we have to decrease the effective stress. So we have the soil in what we call relaxation test. The soil has to increase its pore pressure. So that's it's not a limitation, but it's a specification of the soil behavior. Finally, in some cases, at very low strain rates or high temperatures, microstructuring, so bonding of the soil, may dominate over viscose effects. And that could be a limitation. So, in conclusion, from laboratory observations, clay behavior is controlled by strain rate and temperature. Now, what happens in situ? In the lab, for most common tests, in fact, the strain rate is larger than 3 × 10⁻⁸ So it's in this range. Now in the field, because the layers are much thicker, in fact the strain rates are smaller and usually less than 3 or 2 10⁻⁸ In fact, when we have vertical drains, we see that we increase the strain rate, which makes sense. So the strain rates, typically the strain rates in situ are smaller than the strain rates in the lab. Consequently, in our strain rate model, the compression curve followed in situ should be below the compression curve followed in the lab. Smaller strain rate, effective stress. So it's what we have examined. I remember this figure. So hypothesis A indicates that the compression curve in situ and in the lab would be the same, while hypothesis B indicates that the laboratory curve would be here, while the in situ curve would be below, as shown here. Also, the strain in situ would be smaller with hypothesis A than with hypothesis B. So we have examined this aspect by examining the effective stress strain curves in situ, so under embankment. If we have deep settlement gauges, as for example here, we can define the evolution of strain and strain rate with time. But also if we have the pore pressure, we can define the vertical effective stress and then get the field compression curve, which is the truth. The nature is saying that's a compression curve. And this has been done and compared under 4 test embankments: Berthierville, Gloucester, Saint-Alban, and Väsby in Sweden. And we have in green the compression curve obtained at the end of primary consolidation on high-quality samples, and in red, that's the in situ curve. And we can see that in all cases, the in situ compression curve is below the compression curve obtained at the end of primary on high-quality samples in the lab, which is indicating that at least hypothesis A is wrong. Now, the effective stresses have been plotted in a normalized form here, and we have the rectangulars here for in situ data, and the other points are laboratory data, which is indicating that the in situ behavior is in the continuity or consistent with the laboratory data, and indicating that hypothesis B is the correct one. Now, there are some cases where the data were not so well defined, but we can say that if we have the laboratory curve here in blue and the field curve in green, and if we estimate at a considered strain, if we estimate the pore pressure from the laboratory curve, the excess pore pressure at a given time is LF. But in situ, it should be Fs, with Fs larger than Fl. That's in the logic of the strain rate model. And this can be shown with the case of the Changi Airport in Singapore. Here we have marine clays over about 40 meters, and it's a site which has been reclaimed. That means, in fact, the airport is built over the sea on these clays. And by considering the 24 hours odometer curves and by adjusting the permeability, they came with excellent correlation between settlements and predicted settlements and measured settlements at different depths. But at the same time, they were not able to have such good agreement in terms of pore pressures. And in all cases, the measured pore pressure was larger than the predicted one. which is, again, in the logic of the strain rate model, with the in situ compression curve below the laboratory one. Now, this has been observed in other cases in UK, in the States, in France, and in Sweden. We'll come back to the case of the Vesby test field that I presented before, because we have there an explanation why there is this discussion between hypothesis A and hypothesis B. On the left, you have the figure I presented before, and you can see that there is a difference between the laboratory curve and the in situ curve of about 25 kPa. Okay, Larson and Matson in 2003 reanalyzed the Vesby case and came with these conclusions. Without creep, settlement at the end of primary should be 1.4 meter. That settlement was reached in 1966, so about here, whereas there were still about 30 kPa of excess pore pressures, which is 30 is very close to the 25 we have here, in fact. It's similar. But that indicates that hypothesis A is not correct. More recently, a numerical simulation on the basis of high-quality samples and viscous model gives very good agreement in pore pressures and settlement to Degago et al. So all these data confirm the invalidity of hypothesis A and, in fact, the validity of hypothesis B. However, Mesri et al. In 1985 used the Vesby data to prove that hypothesis A will be correct. For that, they used, in fact, compression curves obtained on 50 millimeter on specimens taken with a 50 millimeter Swedish standard piston sampler. And these specimens were taken in the 60s. And here you have the field, the curve here, and in orange you have a compression curve used by Mesri and Choi. And indeed, the two curves are not very different, which explains why they came to the conclusion that hypothesis A was correct. However, you can see here that the curve obtained on the 200 millimeter in diameter Laval sampler is very different and obtained at much higher stresses. And the explanation is given here. Here we have a compression test obtained with the dash line at the end of primary and the full line after 24 hours. Compression curves obtained with the 200 millimeter Laval sampler in blue and the 50 millimeter Swedish sampler in green. And we can see that the Swedish sampler is disturbing the clay. The pre-consolidation pressure is significantly smaller and the curve is much more rounded. So it is believed that in fact Mesri and Choi got a good agreement because the sampling disturbance was compensating for the viscous effects. Another case is the Kansai International Airport in Japan. It's an airport which has been built offshore Osaka at about 4 kilometers from the shore. And so there was 18 meters of water, 18 meters of very soft alluvial clay, and several hundred meters of Pleistocene clays. These Pleistocene clays are alternating with sand layers, which are more or less draining. So that's the situation, which is quite complex due to these sand layers, which are more or less draining. And so, for building the island, in fact, the alluvial clay has been treated with vertical drains, and in fact, the settlement of alluvial clays was completed in about 6 months. So the long-term settlements are coming from the Pleistocene clays. In fact, Professor Akai calculated settlements on the basis of 24-hour de Meter test and neglecting viscosity or rate effects. He came with a final settlement of 5.9 meters. And here you have the field observations. And in 1994, when the airport was opened, in fact, the calculated settlement was equal to the measured one. So everything was apparently going well. But then you can see that the field settlements are much more important than the predicted one. And the 5.89 meters was reached in 1998. And in 2002, the settlement was 1 meter larger. And in fact, when we look at the pore pressures under the embankment, under the island, in fact, we can see that in this period, the excess pore pressures are still larger than 200 kPa. That's a lot of pore pressures to dissipate, which means that there is still a lot of settlements to come. So, and we think that is consistent with the rate effect observed on Osaka Bay clay, with the result shown here. And we said, in fact, with David Height, that in fact it's another proof that hypothesis A is wrong. We must say, however, that Mesri and Funk last year published a paper analyzing the Kansai airport case, and consider that the end of primary settlement would be of about 9 meters rather than 5.9 meters calculated by Akai, and that hypothesis could be correct. I must say that I doubt about these results. Okay, so there is no doubt in my mind that there is creep during primary consolidation and that hypothesis A is incorrect. Now, what do we do practically to calculate settlements? And my conclusions that I got about 10 years ago are the following. In high compressibility clays, or in cases of well-controlled embankments, or in cases where excessive settlements may have important consequences, viscous effects must be considered during primary consolidation. There are several approaches which can be followed. One is numerical modeling, and there are several models on the market, or add a viscous component called delta epsilon field to the strain calculated on the basis of the 24 hours compression curves. In fact, there are three main questions. The first one is, what is the in situ sigma prime p or sigma prime v y? And what is delta epsilon field that we would have to add to the strain calculated on the basis of the 24 hours compression curves? And the third question is, what is the representative coefficient of consolidation? About the first question, in fact, we compared sigma prime Vy in the field with sigma prime Vy obtained after 24 hours, and we obtained a good agreement for OCRs lower than 2.5. For OCRs larger than 2.5, in fact, the field data are smaller, and this has been explained by the shape of the limit state curves of natural clays. That means also that if you change your 24 hours pre-consolidation pressure by pre-consolidation pressure obtained at larger strain rates, as in CRS test, at that time you could underestimate the pre-consolidation pressure and the settlement. So be careful. Now about delta epsilon field, it has been calculated by Watabe, on the basis of data from Watabe et al. And published with Watabe and myself in 2013. The figure on the left gave the delta epsilon ultimate, because we know there is an ultimate value, versus C sub C over 1 plus E0. And you could examine this to see if delta epsilon field is important or not. If you want more accurate value and more practical one, here is a delta epsilon field versus the strain rate in the field. And for example, for VSB, the viscous strain to add to the settlement calculated on the basis of the 24 hours odometer curve will be of about 6%. Now for normal practice, everyday practice, low compressibility clays, because there are several factors which are, say, fighting against the viscous effects. I mentioned the effect of strain rate first in low compressibility clays is relatively small, but in most cases, in normal practice, we have sampling disturbance. Settlements imply a decrease of the applied total stress with time that is often neglected. Quite often, the water table rises in the embankment, and the 24 hours odometer test already includes some secondary compression. All these factors are to some extent compensating for the viscous effects. So my conclusion is that the rate effects on settlements during primary consolidation are to some extent so compensated and can be neglected when 24 hours compression curve is used in the calculation. So, in conclusion, from now on, do as you have done before, except for special cases. Consolidation. In fact, because CV is high in the over-consolidated domain, the vertical yield stress is generally reached during construction. That means that at the end of construction, generally, the vertical effective stress is on the pre-consolidation pressure profile, which means that on the long term, the pore pressure to dissipate is the one which is shown in green here, in the normally consolidated range, which means that the relevant coefficient of consolidation is the one in the normally consolidated range. From our experience in Eastern Canada, with several sites and several embankments, what happens is that for under embankments, the normally consolidated coefficient of consolidation is typically around 10⁻⁷ square meters per second. In the over-consolidated range, it's typically, I would say, 50 times larger, because in the over-consolidated range, the natural clays are quite stiff. Now, if we consider the CV values obtained in odometer tests and analyzed with the log-T method, the CV underestimates the real value in situ, and typically for our clays by a factor of 10, which is significant. Now about the CV defined with the piezo cone. In fact, it appears that it's somewhere in between, in fact, right in the middle between the the C sub V in the over-consolidated range and the C sub Z in the normally consolidated range. And this has been demonstrated by Faye and Ligo that it's just logical to have this CV between the over-consolidated one and the normally consolidated one. However, as far as embankments is concerned, from experience, it's just useless. Now, main conclusions. In fact, the compressibility of clay soils is controlled by strain rate and also temperature. Isotac hypothesis B provide a consistent constitutive model which applies during both primary and secondary consolidations, and all well-documented cases support its validity. Hypothesis A is incorrect and requires two constitutive equations, one during primary consolidation and another one during secondary consolidation, which is certainly not logical. As demonstrated with the VSB case, it may provide reasonable result when samples are sufficiently disturbed. So, thank you very much for your attention.